Okay, so the final exam is on Tuesday of next week. And like we've discussed before, there's concept questions and problem solving. You can bring a page of notes to use on the second part of the exam, and your computer needs to be capable of running all the software that we've used so far this semester. So are there any questions related to the exam? I'll be in my office today, probably tomorrow, Monday of next week. So if you have questions as you're working through and preparing for the exam, I'd welcome you to stop by, or you can send me an email, and I'll do my best to help you out. Just let me know as you get ready for that exam. Today we're going to be covering a few topics from Chapter 6, very few topics. Unfortunately, groundwater and subsurface hydrology is a topic that you could spend not only an entire semester on groundwater, but you could spend an entire 3-year PhD working exclusively on groundwater issues. And so what we're going to address are just a couple of very narrowly focused topics that you're most likely to see like on the FE exam, or you know, the kind of things that would come up most often in kind of a municipal engineering setting. Now, there are a lot of factors that that play into groundwater hydrology. Hydrology can be focused on trying to figure out the amount of water that is underneath the Earth's surface, the quality of it, and its suitability for use in drinking or industrial purposes, and how that quality is affected by things like contamination. And so there's a really close tie between subsurface hydrology and environmental issues. And then the distribution and movement of subsurface hydrology is important because as we humans continue to use and draw on subsurface resources, then the amount of water and where it's located continues to change. And so we have to shift and adjust how we use that water so that we can continue to have it as a resource for things like the irrigation of crops. Now, the calculations we're going to do today are pretty simplistic, and we'll look at a couple of cross sections where we're assuming that the water is moving through a homogeneous medium, meaning that we're going to assume that the same soil properties apply through the entire width of a well and the entire depth of an aquifer. But you'll remember when we watched that video from the Netherlands that they layered different soil types together, and they kind of illustrate how a heterogeneous soil, how stratified soils can change how quickly the water moves through different types, and it can move sideways because of penetrating layers. And this three-dimensional view is taken from a model that breaks the subsurface up into elements. And so it's a finite element model that would, in this case, is intended to estimate the resistivity of soil. And so that can be like a measurement that is taken as an indicator of how contaminated water could be, you know, like if it has salinity in the water. Other issues related to subsurface hydrology tie into contaminant transport, which is a surface spill, maybe dry cleaning fluid or gasoline or some sort of an environmental pollutant that gets into the groundwater and it starts to move because of the general movement of that groundwater, and we have to keep track of where the plume is and how close it's getting to locations where we have drinking water wells. There are also topics related to trying to improve the amount of infiltration. So engineered storage systems where either you have a flood recharge basin, it's basically a dam that exists specifically to improve the penetration of water down into the subsurface. And in some places, like in Southern California, what they're doing is they're actually taking treated wastewater and they're injecting it underground. And so it's the opposite of a well. It's actually, instead of extracting water from an aquifer, they're pumping water into the aquifer to try and prevent something known as saltwater intrusion, where in a coastal area, the ocean exists both above the bottom of the ocean and below the ocean is also saline water. And if you suck the fresh water underneath the land out, then that salt water can go underground towards the areas that are not under the ocean. And so using injection wells to prevent the intrusion of salt water is kind of a new thing that's been used over the last decade or so. This shows that of all of the fresh water, well, first of all of the water on Earth, 97% of it is in the oceans. And so a very small fraction of the water that exists on this planet is fresh water. And of the water that's usable, most of it is groundwater. And so that just is to underline the importance of subsurface hydrology, that the fresh water we take for granted, like a river right next to our city, is a very small fraction of all of the water that exists on the Earth. We're going to watch a brief video that talks about some of the issues related to the Ogallala Aquifer, which is a big aquifer that exists in the Midwest part of the United States. And it's responsible for a big part of the agricultural productivity in states like Kansas, Nebraska, where crops need to be irrigated. Okay, so we just watched that video about the Ogallala Aquifer. So let me ask you a question. What does the word sustainability mean in the context of what we just watched? What would be sustainable? Okay. All right. Yeah, good point. I guess, like anytime we do a mass balance, what you draw your control boundary, your control surface around, is what you're checking the in and the out over time. And so if you do your control surface around the farms, then sustainable, steady state would mean that the farm can continue at its current level of productivity indefinitely. So that's exactly right. What if we draw the control surface around the aquifer? Then what does sustainability mean there? You don't want a negative accumulation, which means you can only use as much water out of that aquifer as is getting into the aquifer. And so to know that, you can either monitor it with wells and make sure that the level isn't dropping. And they also have models that say for the area, the contributing area where water seeps into the ground and feeds that aquifer, how much rainfall has there been. And that's the only place that the water is going into that aquifer is from the rainfall. And it's not just in the area where you're extracting the water. It may be hundreds of miles away that it rained someplace and raised the water table a little bit over there, and then that caused the water to migrate towards your location because of the elevation in the aquifer someplace else. But I think it's really important for us to think about the resources that we use, how important are they, and therefore how long do we want them to last? Because there's a lot of cases where we use what we want now but don't think long term. Let's look at this groundwater recharge video. So the infiltration rate is improved in the well casing because, number one, the depth, the hydrostatic pressure is higher because the depth of the water is larger as it goes into that well casing. And then the other factor is that there isn't the risk of dust settling and closing off the pores of the soil. They can have like a fine mesh down below. It's not just a pipe with no holes in it. It's a pipe that has serrations and like a fine screen on the outside to allow the water to go through, but not to allow the soil particles inside the aquifer to fall into the well casing. So it's just kind of an illustration of a really simple thing that can be done to try and improve the infiltration capacity so that they can extract more from underground if they're improving the amount of recharge. Now, the one thing you have to be careful about is if that same aquifer is used for drinking, then you're allowing surface runoff to go down into the aquifer, and so its water quality could be compromised. Like if there's animal waste in that field, now the bacteria from that animal waste is in the aquifer. Now, over time, and as the water moves through the aquifer, it'll naturally be cleansed. The bacteria in the soil will break down the bacteria that don't necessarily aren't evolved and adapted to live in soil particles. But over the short term, that contamination can exist, especially if it's things like heavy metals, which aren't going to be broken down by soil bacteria.
Is there anything that can recycle
Yeah. What I've seen is like closed loop systems where you use just a little bit of energy to pump water from underground. Like, you know, during the summertime, the water underground is cool because the soil stays naturally like in the 50s. And so if you dig 300 feet down and you have a pipe that goes down and then up again, you pump a little water through that pipe and it's going to come out cooler than it went in. And so then if you have that water circulating through a series of tubes, think about how a glass of water that has ice in it during the summer is going to have condensation on the outside. So if you want to extract moisture from the air, then that's one kind of low energy application I've seen where you just use like a ground heat sink loop to chill the water, and then it's extracting the humidity from the air that way. And so, I mean, the humidity in the air, some of it's going to be transpired from plants, some of it's just going to be evaporated from the ocean or lakes and so on. But like that's one kind of like gee whiz application that's similar to just digging a hole in the ground, and it's low tech but easy to achieve. Here's a cross-sectional view of an aquifer, and there's some terminology here that you need to be acquainted with. What we're looking at is actually a confined aquifer. And by confined, what we mean is that there's a layer underneath and a layer above the main body of soil that is saturated with water. And that layer up above can cause the water that's beneath to become pressurized. And the reason why it's pressurized is we have a difference in elevation of the ground surface, and recharge occurs over the entire surface, including at this elevated location. And so when there's rain falling on the water surface, it causes the aquifer depth to be perched. And so the water depth is relatively high over here. So if you dig a hole down through and penetrate the confining layer, what would happen is that the water level is going to rise in that well to a certain elevation that's consistent with the pressure of water in the soil at that point. So you'll notice it's a little bit lower than the depth of water right here at A. So at B, the water doesn't rise quite as high because there are energy losses due to the friction of the water to get from A to B. The water's having to flow through the soil to get there, and so there's some losses similar to if it was flow through a pipe. Anytime there's water velocity, there's going to be energy losses. And since the ground level is higher than the water depth at B, then water isn't naturally going to be spurting out of that well. You'd still have to have some sort of a pump to get the water out of that well. But then if we go over to C, what you notice is that the ground elevation is low enough at C that the water would naturally rise to a height that's greater than the ground elevation. And so that's what we call an artesian aquifer, when there's enough pressure at a certain location that the water is going to flow freely. It's a spring. So some of the terms that are shown here, an aquiclude contains water but can't transmit it because of a low hydraulic conductivity like clays. And an aquafuge is rocks, where it doesn't have water and it doesn't transmit water, and so it can still be a confining layer. Rocks can be confining because they have a low or no hydraulic conductivity, but they don't contain water and don't transmit it, unless there are cracks in the rocks. So the artesian aquifer is what's shown here, where there's enough pressure in a confined layer that the water level would rise greater than the surface, and so it flows out freely. An aquitard is another name that we give to a rock or a clay formation that limits the movement of water, and so an aquitard could be a confining layer, or if it's vertically oriented, it could just slow down the movement through the aquifer. A leaky aquifer could be that in this lower confining layer, it could be maybe it's a very thin layer of clay. And so a thin layer of clay is going to slow down the movement of the water above it, but it's not going to totally stop the movement of water. And so the water would go downward, and there may be another confining layer beneath it. There can be, throughout the earth, there could be layers of relatively high conductivity sand, and then a layer of clay, and then silt, and then more sand, and then, so there can be series of lots of different aquifers. You may have to penetrate down through several different aquifers before you get to one that has the water characteristics that you'd like, for example. Did any of you take classes from Dr. McCormick? None of you? Oh, okay. Well, then this story won't mean as much to you, but he has a farm up in Jackson County where he has a relatively shallow well. So the water that comes from his well can be used for hand washing or washing clothes, but it's not deep enough. He hasn't penetrated down through the depth that would be high enough quality for drinking. So the quality of the water is influenced partly how close it is to the surface and what pollutants are getting down through the aquifer. So a leaky aquifer, the water can leak down, but also the water can leak up, which is kind of counterintuitive. But if this is a clay layer or if it's fractured rock, since it's pressurized in the confined layer, water can leak downward, but it could also be migrating up because there's enough pressure to be pushing the water up to this elevation. So that's just something that you need to be aware of, is the aquifer isn't always a complete watertight boundary above and beneath the confined aquifer. Now, remember Darcys Law, where we had some soil column where the cross-sectional area the water is flowing through is known, and we can measure the head of the water upstream and downstream of some known length L. And the difference in how delta H is the driving force that is causing the Q, the flow of water through this column that we're measuring. And so Darcy was the first to suggest that there's some proportionality factor K, and we know it now as the hydraulic conductivity, that related what the flow rate would be based on the cross-sectional area, the head differential, and the length. This also influences how productive a well will be when you drill down into an aquifer and you're trying to find out a certain flow rate out of that aquifer. We use some of the same ideas that are found in Darcys Law. Hydraulic conductivity is a key factor there. Some other terminology, what we're seeing here is an unconfined aquifer. So an unconfined aquifer doesn't have that layer of clay that is forcing the water to not rise. Here we actually have a free surface of water that depresses when we're extracting water from this production well. You can see that discharge means we're taking water from the screened section of the well, and water is moving radially from far away towards the well in all directions. Now think, this is actually a circular, what you should be conceiving of this is a cross-sectional view, and this cone of depression, as it's called, is the closer you get to the well, the lower down the free surface of the water is going to be. And that is, it's kind of a chicken and the egg thing, but the way to think of it is, if you're pumping water out of this well, it has to be coming from somewhere. And so it's coming from all of the soil surrounding it. And so why is the water going this direction? It's going this direction because there's a low spot in the soil. So it's kind of like water flows downhill, right? It flows to where there's the lowest energy. And the depth of the water represents what is the potential energy at that location. And so the water is going to flow from here towards the center of the well because this is where the energy is the lowest. And this is a cone of depression, just kind of gives you an idea of where the water surface is, and the higher the discharge, the steeper that cone of depression. So if it was only 2 liters per second, then maybe as far as this, in order to have steady state of 2 liters per second moving towards that well. So the groundwater shape responds to how quickly the water is being extracted. If you overpump over the long term, then you may have more than just the cone of depression. You may have the water table everywhere generally decreasing as the total volume of water in the aquifer begins to become exhausted. Under static conditions, this line is where the water was before pumping started. And so drawdown is the measurement of where they haven't labeled that correctly. Drawdown is the difference between the static water table and where the water surface is for a certain flow rate. So I'm not sure what they're dimensioning that drawdown to, because the lowest water surface appears to be here at this location in the well. So the drawdown at the well would be from where the static water table height was before pumping started to the water surface in the well. But at some distance r, being the distance, a radius from the center line of the well outward, you can measure the drawdown. And the further away you get from the well casing, the less the drawdown is going to be. Now, the difference, the A versus B, that this is illustrating is that in coarse gravel, for the same flow rate, so we assume that the same discharge is occurring at the well on the left as on the right. What this is showing is that there's less drawdown when you have gravel compared to if you have the water is flowing through an aquifer that is sand. And can you think why you wouldn't need as much drawdown if the water's flowing through gravel than compared to sand? What was the first part of what you said?
Larger voids.
Okay, larger voids, good. So if there's larger voids, then the hydroconductivity is higher, which means you need less delta H, you need less of a driving force to achieve a certain flow rate. Because remember, Darcy's law says Q is K A delta H over L. Okay, so what forces the water, how do you achieve a certain flow rate? Is if you have a low K, low hydraulic conductivity, you need more delta H to force the same amount of water. So here, the driving force is the elevation differential between the water depth in the casing and the water depth at some distance away, like 10 meters away. That's going to be the driving force. And so you don't need as much driving force because there's less friction through the gravel. Bigger voids, it's like a larger pipe. Remember, there's a close analogy between pipe flow and flow through the subsurface, because the soil is like a series of interconnected tubes that the water is flowing through. And if you have a small diameter pipe, you have a lot of energy loss. You learn that in hydraulic engineering. If you have a big pipe, there's going to be less energy loss, so you need less driving force. So that is why, for a coarse gravel with a higher hydraulic conductivity, we'll see a smaller drawdown for the same flow rate, Q. If you overlap two wells together, both of which are discharging, then the cone of depression for both of them ends up being lower than it would be if only one of them was pumping. So this is showing on the left what the cone of depression would be if only well A was producing, then this would be the cone of depression. But then if you turn on an adjacent well, well B, then well B is influencing how deep the water needs to be at A to achieve the same flow rate. So in other words, now you're taking more water out of the aquifer, so it's going to A and water is going to B, so the cones of depression are cumulative. You'd kind of combine together the cone of depression from the drawdown from B and the drawdown from A simultaneously. The wells that we dig to draw water out, both of these wells are fully penetrating, which means the well goes all the way down through the layer that has water in it. And you can see that they don't bother drilling once they get into the confining layer. And this maybe is clay or rock, but once they hit the clay or the rock and they pulled out that soil and they said, okay, we're into clay now, we're done drilling. But it fully penetrates down through the aquifer itself. So that's what we mean by fully penetrating. The screen depth may not be the entire depth of the aquifer. It's where we have the serrations in the pipe. The screen is how much of this pipe can actually have water coming to it. Now, it doesn't have to be screened all the way up, because if it's screened part of the way then those openings are going to hopefully be large enough that the pressure on the outside of the screen is pushing the water in at a rate fast enough that it can flow out of the pump. But the screening is the serrations in the pipe. And then the radius of the well is talking about from the center line, how big is the pipe that you've actually put down into the ground. And the calculations that we'll do, you'll see why it's important that we know the radius or the diameter of the pipe that's used, because it can be one of the locations where we're monitoring how much drawdown there is. And the calculations you're going to learn, you're going to try and predict how much flow, Q, can come out of a well for a certain amount of drawdown. And the drawdown at the well itself is one of the places you can measure drawdown depth. One other factor to tell you about is the transmissivity. And the transmissivity is the product of the hydraulic conductivity, K, for the soil that you've drilled through, and then the depth of the aquifer. And the depth of the aquifer varies depending on if we're talking about an unconfined aquifer, we use the variable B for that. I'm sorry, for a confined aquifer it's B. For an unconfined aquifer it's the height of the water, H. So we'll do an example for both of those. Hydraulic conductivity comes from Darcys Law. The variable K, and it has units of length per time. Aquifer thickness B has units of length. Transmissivity, we just talked about, it's the hydraulic conductivity times the thickness of the aquifer, so it's going to have units of length squared per time. Piezometric head is the sum of the elevation head and the piezometric pressure. So that is where the water is going to rise to a certain level if you penetrate down through a confined aquifer. That's the piezometric head, the first illustration we were looking at, where, you know, if it's an artesian, then the piezometric head is higher than the ground elevation. And then the effective porosity is the fraction of the soil porosity that water can actually flow through because the voids are interconnected. Okay, the simplest case, the easiest calculations to do related to wells is in a confined aquifer. So this diagram is showing you that the thickness of the aquifer here is given the variable B. And so we have a confined aquifer, which means there's a layer of clay or rock both beneath and above the higher hydraulic conductivity. So maybe this is sand or soil or whatever, but how high that aquifer is, the thickness of the aquifer is B. And before we start pumping, the water is at H everywhere. That's the initial piezometric surface. Now the piezometric surface isn't the water height. The water is only up to B. But if we penetrate the aquifer, it's going to rise up to the piezometric surface. And so that's an important point. Here at the well, we drill the well and we don't yet turn on the pump. The water level is going to rise to H before we turn on the pump. But then when we turn on the pump, and it'll take a few minutes or hours to achieve equilibrium, but once it does have equilibrium, then we have this piezometric surface. And the piezometric surface isn't actually the physical height of the water. The water, remember, still isn't going any higher than this upper confining layer. But if you penetrated a well at a certain location, let's say if you put in a monitoring well at 1, just to keep tabs on how high the water level will rise to at that location, then once you start pumping, this is where the water level would be at 1. And so the drawdown would be the difference between the initial piezometric surface and the piezometric surface once the pumping begins. Sometimes this piezometric surface is also called a faradic surface, depending on which book and the terminology. So drawdown here, we're giving the variable S. S is the drawdown at some radius. So these problems will sometimes tell you how much drawdown there is, and then you have to calculate the height of the water, H, at some radius. And H, in this case, for a confined aquifer, it's not the physical height of the water, but it's the height that the water would rise to in a monitoring well. And so it means the piezometric height. So let's practice that. By the way, this is what the equations look like in the current version of the FE reference manual. How many of you are planning to take the FE next semester? Most of you. Good. Well, it's good to become acquainted with that reference manual just to see what format the equations are in and where it's located. The nice thing now is that you can search by keyword. Since the reference manual is available online, you could type in confined aquifer and boom, you're going to go straight to the equations that have confined aquifer, the theme equation. All right, so let's practice this. We have a confined aquifer with the thickness of 6.6 meters, and so that's B, the thickness of the aquifer. The hydraulic conductivity, K, is 20 meters per day. And the initial piezometric surface is 14.53 meters above the confining layer. So that's talking about H. Before any pumping occurs, the water goes up to 14.53 meters. Now what we want to know is what flow rate Q is going to cause the piezometric surface to be lower than that initial value of 14.53. What we're going to do is we're going to measure the piezometric surface at two locations by drilling monitoring wells. And a monitoring well is someplace where you have the well casing going down, but you're not actually pumping water out. You're just using that well to look at how deep the water is. So at a radius of 40 meters, we're going to measure the water depth, and notice that the piezometric surface at 40 meters is 13.85, and then at a radius of 85 meters, it's 14.31. Now let me give you a special caution. 1 and 2 means something very specific. Our convention is that 1 is the location that's closer to the well, and 2 is the location that's further away. So in this equation, you can't flip-flop those. It has to be that 2 is the further location. And so location 2 is going to be R equals 85, and then the height of the water surface will be 14.31 at 2. And then at 1, R is 40, and the H at 1 is 14.85. Okay, so the first step here, part A, is what's the flow rate? And then use the same information to calculate how deep the water is at the well itself if we know this well diameter is 0.5 meters. All right, so I'm going to pause for a moment, give you a chance to do some calculations, and then we'll bring up the solution to make sure everybody's on the same page. .506 cubic meters per day is what you should get for that first part. Wait, yeah, we're doing the confined aquifer first, right? Yeah. So remember, transmissivity is B times K. So to calculate the transmissivity, we had 20 meters per day multiplied by the aquifer depth of 6.6 meters, and that's 132 meters per day. And the convention is that location 2 is always the one that's further away. So that's where the radius is 85. And then the drawdown is less at location 2, because the further away we get from the well, the smaller the drawdown is. And so the height is going to be closer to that original water surface height. The original phoretic surface was up to 14.53 meters of depth before pumping started. So this well is really producing 506 cubic meters per day. Let me give you a moment to solve the second part of that example where you're finding out how deep is the water going to be at the well when you know the well diameter is 0.5 meters. And so the clue there is that's one of the radiuses. What you're essentially doing is you're using the well diameter as R1, and you're solving for H1 with a known Q. Okay, so if you have the well itself as the R1, what we're solving for is the depth at that location. So you can rearrange algebraically the equation to solve for H1 in terms of the known H2 and the flow rate to the well, the ratio of the radiuses and everything. Turns out to be that the water depth at the well should be 10.75 meters when we have the flow rate is 506 and all the other parameters that are described in. So you can see how if we increase the flow rate, then the water depth at the well will get lower.
You can use either monitoring well.
That's right. You can. Good point. I'm glad you asked that. So he's identifying the fact that we could have used 2 or 1. Now, of course, what is 1 and what is 2 changes. You know, like now when we're working with the well itself being location 1, then we call that 1 in the formula. But then we could use either the place where we know it at a distance of 40 or at 85. Either one of those would work. Good. Glad to hear it. You're learning some similar material in 351? Good deal. Yeah. Like I said, this is important in environmental for different reasons. But all right, so this is a confined aquifer. Let's look at an unconfined aquifer. And an unconfined aquifer is a little bit more challenging from a numeric standpoint because we have to square the depths. And the formula in the FE reference manual, it's known as Dupuis formula for an unconfined aquifer, but you know, this is the same as what we're going to have in the example that we work. But what's different is that now when we have a confining layer on the bottom but not on the top, rather than it just being a piezometric surface, it's the actual physical water height rather than the piezometric surface. And the the unconfined aquifer example that we're going to work is we know a flow rate of 0.4 cubic meters per second. Now remember that if the hydraulic conductivity is known in days and the flow rate is given in seconds, you may have to make some changes depending on what's being asked. In this problem, it's just asking you for the hydraulic conductivity, and so you can calculate it in terms of meters per second, since that's the units you're going to have the flow rate in. You don't necessarily have to convert it into meters per day. But, all right, so we know in this problem it tells you the drawdown. Now, drawdown and H aren't the same thing. And so capital H is where the water was before pumping. Drawdown is the distance between the water surface and capital H. And so in this problem statement, what we're saying is 50 meters from the well, the drawdown is 1 meter. And so H1 is going to be capital H minus the drawdown. So in other words, lowercase h1 is capital H minus the drawdown S1. And H2 is capital H minus the drawdown at 2, where the drawdown at 2 is S sub 2. So calculate the hydraulic conductivity. K is the unknown in our first problem, A. And then in B, find out what would be the drawdown 5 meters from the well. So that's at a new R distance. We want to solve for the drawdown. And so remember, this formula isn't going to tell you the drawdown directly. It's going to tell you the H. So you calculate the H, and then from that, you'll get the drawdown. For the first part, the hydraulic conductivity for the unconfined aquifer. All right. So labeling the one, what is location 1 and what is location 2? The convention is location 2 is the one that's further away. Location 1 is the one that's near. And so if you're given the drawdown, you need to calculate the H at both of those locations by starting with the initial height of the water above the bottom of the aquifer. And then if we just rearrange algebraically to solve for K, the hydraulic conductivity, then what we get is the hydraulic conductivity should be 3.8 times 10 to the minus third meters per second. And then as to the expected drawdown, 5 meters from the well, I'm not able to display that on the screen, but it's there on the whiteboard, so we already talked through isolating that variable h1 algebraically is maybe more effort than it's worth, and so that's why I just put it into solver and solved for it. But yeah, so the solution, the h1 is 21.26 and the drawdown 2.74 meters. Any questions about that? Well, I've got a question for you. Why do you think we're squaring the H values for an unconfined aquifer, whereas in a confined aquifer, we didn't square it? Well, remember, in the confined aquifer, the water's not moving vertically. It's just that piezometric surface that has the drawdown. So the water is only moving horizontally in the confined aquifer. And so the best I can figure is that the H squared accounts for the fact that the water is traveling both horizontally and downward towards the well. And so you notice that like these arrows, which are indicating the flow direction, also have a downward slope to them. And so the driving force is what this distance accounts for. You know, how much energy is available to drive the flow towards the well. And if it's only a horizontal movement, there's going to be more energy available because you didn't have, if you think about the flow path, you only have a lateral flow path towards that well. But down in this situation, you've got a longer distance, and so there's less energy available. And so squaring that, each of the individual water heights, I think accounts for that effect. Did you have a question?
I did, and I actually figured it out.
Okay.
I was asking why we were using K instead of T. I
Ah.
realized that there's no confined aquifer, so there's no thickness.
Right. Good. Yeah, so if you want to practice those are good FE questions because they're just bite-sized. And increasingly, the FE questions that are being written these days are problems that can be solved in 3 minutes, where we used to write questions for like up to 8 minutes. They're a lot shorter these days, and these happen to be good candidates for relatively quick questions. One other thing I want to show you, but we won't actually do some calculations for, is the formulas that describe the flow between reservoirs. And so if you have two lakes that are some distance apart, water's going to flow from the elevated lake towards the lower lake. And this model says, let's even complicate things further by having two different soils. There's soil type 1 up above, soil type 2 beneath, and they have different thicknesses and different hydraulic conductivities. So an actual location where I can think of this, where there's like two ponds next to each other, is near the cemetery that's on Route 60, like by the Subaru dealership, or like by Kmart. There's a couple of lakes, and they have different elevations there, and so water is going to be flowing from the upper lake towards the lower lake. What this formula tells you is for a unit length, so think into the page, for 1 meter, how you could calculate the flow per unit thickness into the page with the height differential between the lake on the left and the lake on the right, the different hydraulic conductivities and so on. So subsurface hydrology is really complicated stuff. I took a class in subsurface hydrology when I was working on my PhD, and it's far and away it was the most challenging course that I had in my entire career there. So we're not going to actually do this from a calculation standpoint, but I just want to make you aware that things get deep really pretty quickly. All right, we're out of time for today. The course evaluations are open, and I'd be grateful for your feedback on the course, so I'd encourage you to go to MyMU. I don't care if you do your evaluations for the other classes, just do them for this class, all right? This should be your top priority. Because I actually, I've made changes into how I teach based on student suggestions. The lecture videos,